On April 14th, 2026, Blackmagic Design announced DaVinci Resolve 21, and one line in the release quietly challenged an old assumption. The same professional finishing environment was being built for Mac, Windows, and Linux, but the most interesting story was happening behind the interface. Across high-end post houses, color suites, visual effects departments, and render rooms, Linux was no longer the strange machine in the corner. It was becoming the operating system underneath some of the most expensive creative hardware in the building, often without clients ever noticing. That sounds like a recent rebellion against Windows and Mac OS. It is not. In professional post-production, Linux has been hiding in plain sight for years. The surprise is not that Linux can edit video. The surprise is how many modern bottlenecks make its old strengths suddenly more valuable. An 8K timeline can push billions of pixels through decode engines, GPU memory, system RAM, storage, effects, scopes, and encoders every minute. At that scale, the operating system is not decoration. It is the traffic controller deciding which process runs, where memory lands, and what interrupts first. But there is a catch. The popular explanation that Linux is faster simply because it has less telemetry is far too convenient. Windows and Mac OS do run background services, yet they are not secretly throwing away half the performance of a workstation for no reason. If Linux is winning in certain rooms, the advantage has to come from somewhere deeper than a few disabled services and a cleaner desktop. The clue appears when a workstation stops looking like a personal computer and starts looking like a small compute server with monitors attached. Multiple GPUs, huge memory pools, dedicated NVMe arrays, high-speed shared storage, capture hardware, reference displays, remote render nodes. Now the question changes. Which operating system gives engineers the most control over how every one of those resources is assigned? That is where Linux becomes dangerous to the old assumption that professional video work belongs naturally inside a proprietary desktop ecosystem. The shift is also easy to miss because it is not happening equally across the entire editing profession, or for the same technical reasons. A freelance Premiere editor on a laptop and a colorist feeding 4 GPUs from a machine room are solving completely different problems. A television editor locked to Avid workflows and a VFX supervisor launching hundreds of background jobs are not choosing an operating system for the same reasons. Linux becomes most compelling exactly where the workstation turns into infrastructure, and the creative application becomes one stage in a larger pipeline. That distinction explains why the switch can look invisible from the outside while feeling obvious to the engineers building the fastest systems, and it leads to a more uncomfortable conclusion. The future of high-end editing may depend less on the desktop people see than the compute fabric beneath it. To understand why, follow a single frame through a modern post-production workstation. Before it can be graded, stabilized, denoised, composited, sharpened, reframed, and exported, it has to be read from storage and decoded. Then pixels move through memory, affects kernels, caches, and often multiple hardware engines before the finished image is encoded again. At ordinary resolutions, inefficiencies can hide inside spare capacity. At 8K, high frame rates, raw media, spatial noise reduction, optical flow, AI masks, and multi-layer compositing, they become visible. A tiny stall repeated across millions of operations becomes a dropped frame, a sluggish viewer, or another hour added to a render queue. This is why a serious comparison cannot begin with the desktop theme or idle RAM usage. It has to begin with the data path. Modern NVIDIA GPUs contain dedicated hardware for video decoding and encoding, separate from their general CUDA cores. Those fixed function blocks can accelerate formats such as H.264, HEVC, and AV1 without asking the CPU to brute force every frame. On current Blackwell hardware, the video engine also adds professional 4.2.2 encode and decode capabilities. That matters because 4.2.2 acquisition is common in production cameras, and moving that work into dedicated hardware can change the feel of an entire timeline. But crucially, NVIDIA exposes these video engines on both Windows and Linux, so the first myth collapses. Linux does not win because it possesses a secret encoder that Windows lacks. If the same application, driver, GPU, codec path, and media are used, the hardware doing the heavy lifting may be nearly identical. The operating system advantage appears around that hardware, how predictably the rest of the machine can feed it. Linux gives administrators unusually direct control over CPU affinity, memory placement, device access, process priority, power policy, background services, and interrupt behavior. On large, multi-socket or high core count machines, those controls are not cosmetic. They can determine whether a thread repeatedly crosses memory boundaries or stays close to the data it needs. Modern high-end CPUs use NUMA, non-uniform memory access, in which memory attached to one part of the processor topology can be faster for nearby cores than for distant ones. Linux control groups and CPU sets can bind workloads to selected CPUs and memory nodes. For ordinary editing, this can be overkill. For heavily engineered systems, it can reduce contention and make performance more repeatable. Linux can also isolate CPUs from ordinary scheduler activity and move interrupts away from chosen cores. Kernel features, such as no sundas, full reduce recurring scheduling ticks on selected CPUs, specifically to reduce operating system jitter. These tools were designed for real-time and high-performance computing, not for making a YouTube timeline feel 10% faster, but the philosophy maps perfectly to demanding media systems. A post house can reserve cores for latency-sensitive audio or I/O tasks, keep render workers on another group, and leave housekeeping activity elsewhere. It can assign GPU jobs, automate cache locations, constrain services, or launch background processes with carefully defined resources. The gain is not one magical benchmark number. The gain is control over worst-case behavior. That distinction matters because professional editors often care about consistency more than an impressive peak score. A system that renders one test 2% faster but randomly interrupts playback during a client session may be worse than a system with slightly lower peak throughput and far tighter behavior. In a grading theater, a single unexplained hitch can matter more than a synthetic benchmark victory. This is where the idea of a custom real-time Linux kernel enters the story, and where another exaggeration needs to be removed. The preempt RT work in Linux changes locking and interrupt behavior to reduce scheduling latency and make the kernel more preemptible. It is powerful technology, especially for real-time audio, control systems, and workloads where response deadlines matter. But a real-time kernel does not automatically make an 8K export finish faster. Lower latency and higher throughput are different goals. Aggressive preemption can even introduce overhead in workloads that simply want maximum sustained compute. A render that saturates every GPU for 40 minutes may benefit more from stable drivers, fast storage, correct NUMA placement, and good application scheduling than from a real-time kernel. The same applies to stripping background services. A minimal Linux installation can reduce unwanted activity, but deleting every daemon is not a substitute for understanding the workload. The largest speedups in professional video usually come from putting the right work on the right hardware. Hardware decode, GPU effects, fast cache drives, enough VRAM, sufficient memory bandwidth, and an application designed to exploit them. This is why DaVinci Resolve is so important to the Linux story. Resolve is not an open source editor built as an ideological demonstration. It is a commercial finishing system used for editing, color, visual effects, audio, and delivery. Blackmagic ships it across Mac, Windows, and Linux, which means a facility can evaluate Linux without abandoning the creative environment its artists already know. In 2026, Resolve 21 continues that cross-platform strategy while pushing further into immersive workflows, background processing, AI-assisted tools, and high-end finishing. The existence of a full Linux version removes the single biggest barrier that stopped many creative professionals from taking Linux seriously, the absence of a flagship application capable of living at the center of the pipeline. Yet even here, the story is not install Ubuntu and everything becomes faster. Blackmagic's Linux support has historically been much more controlled than the anything goes culture of consumer Linux desktops. Supported distributions, drivers, codecs, and hardware combinations matter. A workstation built for paid finishing is treated more like an appliance than a weekend experiment. That is a recurring theme across the professional graphics world. Foundry qualifies Nuke and Hero on Rocky Linux. The VFX reference platform publishes annual targets for compilers, core libraries, Python, Qt, OpenColor.io, OpenEXR, OpenVDB, and other components, so applications from different vendors can coexist inside complex studio pipelines. The VFX reference platform says Linux is the primary operating system on artist workstations at many studios. That fact is older and more significant than any recent social media trend. Linux did not suddenly arrive because creators became angry about telemetry. It inherited a culture of workstation computing from the era when visual effects facilities relied on expensive Unix systems such as Silicon graphics machines. When those proprietary Unix workstations faded, Linux offered something studios desperately wanted: familiar Unix-like tooling on commodity x86 hardware. Artists could use graphical applications, while engineers could script, automate, mount shared storage, deploy render jobs, manage permissions, and reproduce software environments using the same underlying operating system across workstations and servers. For a small creator, that difference may be irrelevant. For a facility processing terabytes of camera originals, maintaining dozens of identical seats, running overnight renders, and handing shots between editorial, color, compositing, and delivery, consistency becomes an economic advantage. Every unusual machine state becomes support time. Every manual configuration becomes a future failure waiting to happen. Linux makes aggressive standardization possible. A studio can define the operating system image, driver branch, application versions, mount points, color management libraries, fonts, plugins, environment variables, and security policies, then deploy that known state repeatedly. When a project starts on one machine and continues on another, the operating system becomes part of the pipeline contract. This is the real meaning of bloat in a professional environment. It is not merely a few gigabytes of pre-installed software. Bloat is anything outside the production requirement that can update, notify, index, scan, synchronize, reboot, steal I/O bandwidth, modify a driver, change a codec path, or produce a support variable an engineer did not authorize. Windows can be managed tightly in enterprise environments, and macOS can be administered at scale. Neither platform is inherently incapable of professional control, but Linux exposes unusually deep layers of the system and allows a facility to remove or replace large parts of the user space stack without fighting the assumptions of a consumer desktop product. The network side becomes equally important. High-end post increasingly depends on centralized storage instead of files sitting on one internal drive. Uncompressed or lightly compressed high-resolution media can demand enormous sustained throughput. Multiple artists may read from the same storage fabric while renders and proxies are written back simultaneously. At that point, network tuning becomes part of editing performance. Linux has deep roots in server networking, storage, and high-performance computing, so the same platform can be tuned from the NICQs upward. Engineers can control interrupt affinity, queue behavior, file system choices, caching policies, and service placement. Again, none of this means a default Linux installation automatically outruns a tuned Windows workstation. It means the ceiling for deliberate engineering is very high. Then there is GPU scaling. Perhaps the most visually obvious reason high-end users notice Linux. A colorist or compositor is not always asking whether one GPU is 5% faster. The real question may be whether the workstation can host several large GPUs, feed them enough PCIe bandwidth, cool them continuously, address enough VRAM, and keep the software stack stable through marathon sessions. This is where modular x86 Linux workstations differ philosophically from tightly integrated systems. The builder can choose massive cases, workstation motherboards, high wattage power supplies, specialized capture cards, enormous RAM capacities, multiple storage controllers, and discrete GPUs. Windows can use much of the same hardware, of course. The Linux argument is that the hardware freedom can be matched by software freedom at the system level. macOS takes almost the opposite approach. Apple controls the hardware and operating system together, and Apple Silicon integrates CPU, GPU, media engines, and unified memory with remarkable efficiency. For editors working heavily in codecs and applications optimized for that architecture, a Mac can be extremely difficult to beat in performance per watt, acoustics, portability, and setup simplicity. That is why the idea that professional editors are abandoning macOS because Linux is universally faster does not survive contact with real workflows. Final Cut Pro remains a macOS application. Adobe Premiere remains officially targeted at Windows and macOS, not Linux. Entire plugin libraries, control surfaces, audio tools, ingest utilities, and client workflows may depend on those ecosystems. As of August 2026, Adobe's current Premiere requirements list Windows and macOS platforms, not Linux. That single fact blocks a straightforward migration for millions of editors. You cannot replace the operating system while keeping every creative dependency unchanged. The cost of retraining, project interchange, plugin compatibility, fonts, codecs, and collaboration can overwhelm any theoretical performance gain. So who actually moves? The strongest candidates are professionals, whose core applications already support Linux and whose bottlenecks resemble compute infrastructure. Resolve colorists, finishing artists, compositors, VFX editors in Hyro, pipeline-heavy studios, scientific visualization teams, virtual production departments, and facilities that combine editing with rendering, transcoding, or machine learning workloads. For them, Linux can remove a category of friction that rarely appears in consumer reviews. Headless operation is normal. Remote access is normal. Scripting every repetitive operation is normal. Launching jobs without a visible desktop is normal. Reproducing the same environment on another workstation is normal. Treating a GPU as a schedulable compute resource rather than merely a display device is normal. Linux fits that culture because change can be explicit. Long-lived enterprise distributions such as Rocky Linux are attractive not because their packages are always newest, but because studios can build around a predictable base. Foundry's qualified Linux targets and the VFX reference platform exist precisely because latest everything is a terrible strategy when dozens of expensive applications must share one machine. Custom kernels still have a place, but usually for a measurable reason. An engineer might need specific hardware support, latency behavior, scheduling features, or security configuration. CPU isolation can reserve cores, frequency policy can favor performance, real-time preemption can reduce latency, but each tweak is a trade. The professional advantage is the ability to make the trade consciously, test it, and keep it reproducible. That is different from claiming Windows or Mac OS intentionally throttle rendering for stability. All three platforms manage power, thermals, scheduling, and responsiveness. A workstation cannot violate the electrical and thermal limits of its CPU or GPU simply because it runs Linux. If cooling is inadequate or firmware imposes a power ceiling, the kernel cannot negotiate with physics. A fair benchmark, therefore, has to be almost painfully controlled. Same motherboard, same CPU, same RAM, same GPU, same firmware, same storage, same media, same project, same application build where possible, equivalent GPU drivers, equivalent power policy, equivalent cache state. Then measure timeline playback, render time, export time, frame time variance, dropped frames, and system power. Even that test can produce different winners depending on the codec. One platform may have a better hardware decoder path for a camera format. Another may have a better GPU driver for a particular effect. A third may dominate ProRes workflows because of dedicated media engines. The operating system label alone explains less than benchmark headlines often imply. The same is true of 8K. 8,000 horizontal pixels sounds like a single workload, but it is not. 8K H.265, long GOP footage, 8K RAW, 8K EXR sequences, and an 8K timeline filled with temporal noise reduction are radically different problems. One stresses decode hardware, another storage, another GPU compute, another memory capacity and bandwidth. This is why serious editors stop asking which operating system is fastest. They ask, which stack is fastest for my media, my effects, my delivery format, and my failure tolerance? Linux becomes compelling when the answer benefits from customization and scale. Mac OS becomes compelling when integrated media hardware and creative software alignment dominate. Windows becomes compelling when software breadth and peripheral compatibility dominate. Privacy comes from architecture and policy, not from a penguin logo. A studio can segment networks, restrict outbound traffic, isolate sensitive machines, control updates, and audit services on multiple operating systems. Linux simply gives engineers a particularly transparent and programmable environment for building those controls, especially when it already matches the rest of the infrastructure. The financial case is therefore not free software saves money. Many of the applications driving Linux adoption are expensive proprietary tools. The economic advantage appears when standardization, automation, remote management, hardware utilization, and reduced support variance save hours across many artists and many projects. One avoided day of downtime can matter more than years of desktop licensing. There's another reason the change remains quiet. The person choosing the operating system may not be the editor. In a large facility, pipeline engineers, systems administrators, color scientists, VFX supervisors, and CTOs influence the workstation image. The artist may simply log in and open Resolve, Nuke, Hero, or another approved tool without caring which kernel booted underneath. That makes Linux almost invisible when it succeeds. Nobody posts a victory screenshot because the machine did what it was supposed to do. The client watches the reference monitor, not the taskbar. The colorist touches a panel. The compositor moves nodes. The editor scrubs a timeline. The operating system disappears behind the work. And disappearance is the ultimate goal of a production workstation. The best system is not the one with the most interesting desktop. It is the one that keeps playback real time, keeps color transforms correct, keeps storage mounted, keeps the GPU fed, keeps audio synchronized, and keeps rendering long after everyone has gone home. Multiple GPUs are useful, but only when the application can distribute work across them and the PCIe topology does not become the bottleneck. Fast NVMe is useful, but only when the media pipeline can read and write without contention. Linux gives engineers tools to observe and shape those relationships, but it cannot rescue software that was never designed to scale. That final limitation is important because the operating system does not edit the film. Applications do. If the editor depends on Final Cut Pro, Linux is irrelevant. If a newsroom depends on a specific Avid deployment, migration may be impractical. If a production lives inside Adobe Dynamic Link and a collection of proprietary plugins, the strongest Linux workstation in the world may be the wrong machine. But when the creative stack is portable, the calculation changes rapidly. Resolve can sit next to Nuke. OpenColor I/O can keep color transforms consistent. EXR, OpenXR libraries, ACS workflows, shared storage, Python tooling, and render infrastructure can live inside a common technical culture. The workstation starts to resemble the rest of the studio instead of an exception to it. The 2026 VFX reference platform makes that culture visible. Its job is not to crown Linux the fastest desktop. It defines compatible versions of compilers and libraries so software vendors can target a shared environment and studios can reduce incompatibilities. In other words, one of Linux's strongest professional advantages is not speed at all. It is coordination. Coordination sounds boring until a deadline is collapsing. A plugin compiled against the wrong library, a color management mismatch, a driver regression, or a mount failure can stop a six-figure production faster than a slow benchmark. High-end Post is filled with systems whose value comes from being predictable together, not individually impressive. That is why Linux's old reputation as a system for engineers can become an asset instead of a liability. The terminal is not there because artists should suffer. It is there because the entire workstation can be described, inspected, scripted, and repaired at a level that scales beyond one person sitting at one screen. Automation follows naturally. Media can be copied, checksummed, transcoded, proxied, indexed, analyzed, rendered, and delivered through scripts or services. Background jobs can run on the workstation, then move to dedicated nodes. Containers can package tools. Remote render commands can launch without a GUI. Logs can be collected centrally. Failed jobs can be retried automatically. None of this means the migration is painless. Driver installation can fail. A kernel update can break a module. Audio devices may behave differently. Consumer capture hardware may have weak Linux support. Some codecs or delivery formats can require different workflows. Plugins may not ship Linux binaries. Vendor support may insist on one certified distribution instead of the one an artist prefers. The cost of that friction is why high-end facilities qualify machines instead of casually switching. A professional Linux workstation is frequently more engineered than a consumer Windows or Mac setup, not less. Someone has to choose the distribution, validate the GPU driver, test the I/O hardware, confirm the codecs, manage color, lock versions, and document recovery procedures. That investment only makes sense when the return is real. For a freelancer whose entire workflow fits elegantly inside a MacBook Pro, it may not be. For an editor whose business depends on Premiere and After Effects, it probably is not. For a facility whose core work already lives in Resolve, Nuke, shared storage, and scripted pipelines, the return can be substantial. This is the point where switching to Linux stops meaning replacing a Windows icon with a Linux icon. It means changing the workstation's identity. Instead of a general-purpose personal computer that also edits, it becomes a controlled production endpoint designed around a defined set of media tasks. Once that happens, the operating system can be trimmed, tuned, monitored, and frozen around those tasks. CPU cores can be partitioned. Memory behavior can be observed. Services can be constrained. Storage paths can be standardized. Drivers can be pinned. Remote management can be automated. The machine becomes less personal and more intentional. And that is probably the real source of the performance stories. Not that Linux contains a hidden reserve of silicon power, but that a carefully engineered Linux workstation encourages people to account for the entire pipeline. When every bottleneck is visible, there are fewer places for accidental inefficiency to hide. The best Linux workstation may not beat the best Mac or Windows workstation on every benchmark. It does something more useful for a certain class of professional. It allows the facility to decide what best means, then shape the system around that definition. That is why the movement feels less like a consumer operating system war and more like the return of the workstation. The workstation was never supposed to be a generic machine. It was a purpose-built instrument, expensive because every component existed to serve a professional task. Linux fits that idea almost perfectly. It can be ordinary when it needs to be, but it can also be stripped into an appliance, expanded into a server, hardened into a restricted endpoint, or tuned into a low-latency compute node. The same operating system can stretch from an artist's desk into the machinery behind the building. The April 2026 release of Resolve 21 did not create that reality. It simply made the contradiction harder to ignore. One of the world's most capable finishing applications still treats Linux as a first-class desktop platform at the same moment the broader VFX industry continues standardizing around Linux workstations. Meanwhile, the barriers remain obvious. Adobe editors cannot simply carry Premiere across. Final Cut users are tied to Apple hardware and Mac OS. Specialized plugins and devices can dictate the platform before a benchmark even begins. Linux is not replacing every professional editing system, and pretending otherwise hides the more interesting transformation. The real shift is happening at the high end, where editing overlaps with grading, compositing, rendering, storage, automation, and infrastructure. There, the operating system is no longer chosen for familiarity. It is chosen for how well it can disappear into a controlled technical pipeline. That is why some professionals are moving quietly. They are not chasing an ideology, and they are not unlocking performance that Microsoft or Apple deliberately hid. They are building machines where every core, GPU, disk, driver, process, and update can be treated as part of the production design. In that environment, Linux does not win because it is free, private, or fashionable. It wins when control itself becomes a performance feature.